Hello, folks. How y'all doing? Let's start section 6.1. So we're going to define the dot product of two vectors. The answer that we get is a scalar, and in a moment we'll talk about what that scalar represents. We can use that scalar to represent the angle between A and B. To find the dot product of two vectors, we multiply the matching components and then add the results. You may have seen this operation in another class. So as an example, if we want to find the dot product of the two vectors 3, 2, which is right here, and negative 4, 1, which is over here, we calculate the product of the x-coordinates. 3 times negative 4 is negative 12. 2 times 1 is 2. The answer is 10, or negative 10. And the question is, what does this negative 10 represent? Well, it tells us something about the angle. If the dot product of two vectors is positive, the vectors form an acute angle. That is, if the dot product is positive, the angle is in quadrant 1. If the dot product of two vectors is negative, the vectors form an obtuse angle. And if the dot product is exactly 0, the vectors form a right angle. We know another function that does the same thing, the cosine function. Is positive in quadrant 1 and negative in quadrant 2. And it turns out that the dot product and the cosine are measuring the same thing but in different units. And therefore, if all we do is apply a conversion factor, we can convert dot products to cosines. And that's what the next page does for us, is that we have a formula. The conversion formula is just the magnitudes of the vectors that we're applying here, and that converts from a dot product to a cosine. And so the exact angle between two vectors, we can calculate that by taking the dot product of the two vectors, scaling out the magnitude of the vectors that we are dot producting, and that gives us the cosine of the angle. Then we can take the inverse cosine to find the answer. We'll do an example of that in this slide right here. Let's find the angle between these two vectors here, 3, 2, 0 and 1, 4, 1. So the first thing we'll do is we'll calculate their dot product. 3 times 1 is 3. 2 times 4 is 8. And 0 times 1 is 0. When we add those together, we get an 11. That will be the numerator in our product. And then our denominator is to be the magnitudes of the two individual vectors. 3 squared plus 2 squared plus 0 squared. 1 squared plus 4 squared plus 1 squared is square root of 18. So when we divide that out, we get 0.719. And so the angle is the inverse cosine of this number, which is about 44 degrees. So just sketching what we've done here, the angle, the vector 3, 2, 0 is 3 units out in the x direction and 2 units over in the y direction. So it's roughly right here. And then 1, 4, 1 is 1 unit in the x direction, 4 units in the y direction, so that's roughly about here, and then 1 unit up in the z direction. And so that's got to be about this vector right there. The angle between those two vectors is just under 45 degrees. All right. So the dot product is the numerator, the magnitudes are the denominator, and the answer is the inverse cosine of the cosine of the answer. We have to take the inverse cosine to get the answer. So let's move on. We say that a set of vectors is an orthogonal set if every pair of vectors in the set is orthogonal. Orthogonal means the angle is 90 degrees, or another way of saying that is that the dot product is 0. So here's an example of an orthogonal set. These three vectors form an orthogonal set. To check this, every pair of vectors has to be orthogonal. So v1 dot v2 has to be 0. Well, that is negative 3 plus 2 plus 1, and that's 0. v1 dot v3 has to be 0. That's negative 3 halves. 1 minus 2 times minus 2 is negative 2. 1 times 7 halves is plus 7 halves. So that's negative 3 halves minus 4 halves plus 7 halves. That's 0, so this checks. And 2 and 3 have to be orthogonal. So negative times negative is going to be positive 1 half. 2 times negative 2 is going to be negative 4. 1 times 7 halves is 7 halves. So the positive terms add up to 8 halves, which cancels with the negative 4. And so all three vectors are orthogonal. If we were to graph this, this would look like an x, y, and z axes that are all perpendicular to each other, but sort of floating around at some angle that, are not, vertical and horizontal, that this is at some angle, this is at some angle, this is some angle. And so we get like three perpendicular vectors, but they're just, rotated somewhere in space. But that's an orthogonal set. We have a theorem that says any orthogonal set that does not include the 0 vector is linearly independent. So 0 dot product with anything is 0, and so 0 doesn't give us much information. But any orthogonal set that doesn't include the 0 vector is a linearly independent set. And because it's linearly independent, a basis for a vector space that's orthogonal is called an orthogonal basis. And so it's just any basis for that space that's also an orthogonal set. And then we get to our kind of a mathy theorem, but let's talk through this math here. If we have an orthogonal basis for subspace, then we can convert from standard to alternate coordinates using a dot product formula. So right now in chapter 3, we learn how to convert between standard and alternate coordinates. This works for all bases. If we want to go from alternate to standard, we just had to multiply out a linear combination. Take the first thing times u1, take the second coordinate times u2, the third coordinate times u3, and so on and so forth. Just expand a linear combination. But if we wanted to go from standard to alternate, we had to augment a matrix. We put the vectors in the alternate basis on the left. We put the alternate basis on the right. We row reduced, and then we solved for v. This works for all bases. For orthogonal bases, we can use this dot product formula to go from standard to alternate. Which is faster than row reduction. This is an advantage of orthogonal bases over other types of bases. So the dot product is where we will take the dot product of the standard vector coordinates with the alternate bases vectors over the dot product of the alternate bases vectors with themselves. So v dot u over u dot u. All right. So let's try this out. We have already seen that this is an orthogonal set of vectors. So we want to then take this vector v and rewrite it in the form of a linear combination of vectors in B. So we want to find the alternate coordinates of this vector. All right. So we're going to have 3 coordinates to find. So we're going to multiply we're going to do the dot product of v with v1 over v1 dot with itself. Let me just erase that. Try this again. Sorry. All right. So the dot product of both vectors is 18 plus 1 is 19, minus 8 is 11. And the dot product of v1 by itself is 9 plus 1 plus 1, which is also 11. So our first coordinate is 1. So for the second coordinate, that's v dot v2 over v2 dot with v2. So this time we're taking this vector and this vector and dot producting them together. So that's going to be negative 6 plus 2 is negative 4. Negative 4 minus 8 is negative 12. And then in the denominator, we're going to just do v2 with itself. So that's going to be negative 1 times negative 1 is 1. 1 plus 4 is 5. 5 plus 1 is 6. Negative 12 over 6 is negative 2. And then for the third coordinate, we're going to take v with v3, this vector and this vector together. So 6 times negative 1/2 is negative 3. Minus 2 is negative 5. Minus 8 times 7 over 2 is 28. So negative 5 minus 28 is negative 33. All right, and then the last one, because it's got fractions, I'm going to go ahead and write out v3 dot v3. Negative 1/2 times negative half is 1/4. Negative 2 times negative 2 is 4. 7 halves times 7 halves is 49 over 4. So 1 plus 49 over 4 is 50 over 4, which is 25 over 2. And then 4 is 8 halves, and so that's 33 halves. Negative 33 divided by 33 halves is negative 2. And so what that says is that the vector v, now we're going to write this as a linear combination, is 1, the weight 1 times the first vector, minus 2 times the second vector, minus 2 times the third vector. Well, look at that. Let's see if that works. In the top row, we get 3 plus 2 is 5. Negative times negative is positive 1. So that's 6. In the middle row, we get 1 minus 4 is negative 3. Negative times negative is positive again. That's plus 4. Negative 3 plus 4 is 1. And then the bottom row, we get 1 minus 2 is negative 1. Minus 7 is negative 8. So that checks. And so we converted from standard coordinates to alternate coordinates. And instead of row reducing, we just had to work out a bunch of dot products and solve some fractions. All right. So if you thought that was easy, we're going to come up with another type of basis that makes this even easier. It's called an orthonormal basis. An orthonormal basis is a basis in which every pair of vectors is orthogonal and all the vectors have a length of 1. So all of the vectors are scaled to be unit vectors. So as an example, this is an orthonormal basis. The dot product is 0. So this is going to be 1 over the square root of 18 minus 2 over the square root of 18 plus 1 over the square root of 18 is 0. And so that's orthogonal. But the magnitude of B1 is the square root of, then we square all these coordinates, we're going to get 1/3 plus 1/3 plus 1/3. And that means that's just a square root of 1. And so B1 is a unit vector. And the magnitude of B2 is the square root of square all of these. So we get 1 over 6 plus 4 over 6 plus 1 over 6 is the square root of 1. And so B2 is a unit vector. And so we have an orthonormal basis. That's what we were given in example 5, and it checks out. This is an orthonormal basis. Why is an orthonormal basis faster for a computer to work with than just a regular orthogonal basis? Is because in the formula v dot b1 over b1 dot b1, for example, that we use to find the coordinates, the denominator is always 1. 1 over root 3 times 1 over root 3 is 1/3. The middle coordinate times the middle coordinate is 1/3. The last coordinate times the last coordinate is 1/3. When we add them together, we get 1. And so in a computerized context, if we're writing code, we can cut the number of instructions in half because the denominator is always going to be 1. And so that speeds up our code by a factor of 2. For humans, these numbers are not pretty to look at, but for computers, we can cut down the number of instructions by using an orthonormal basis. All right. So with that in mind, let's try this last example. If we have an orthogonal set, and we've seen this set a couple of times today, construct an orthonormal basis from them. So we want unit vectors. So our first unit vector, we're going to divide this by the magnitude of the vector. So the magnitude of v1 is going to be the square root of 9 plus 1 plus 1, which is the square root of 11. So our first unit vector is going to be 3 over the square root of 11, 1 over the square root of 11, and 1 over the square root of 11. Then the magnitude of v2 is the square root of 1 plus 4 plus 1. That's the square root of 6. And so our second unit vector is negative 1 over root 6, 2 over root 6, and 1 over root 6. Oh, and then for the last one, the magnitude of v3 is the square root of 1/4 plus 4 plus 49 over 4. We did that calculation before. Those fractions add up to 33 over 2. And so our third unit vector is negative 1/2 divided by the square root of 33 halves, and negative 2 divided by the square root of 33 halves, and 7 halves divided by the square root of 33 halves. And you can simplify these fractions a little bit if you want to, but it's not necessary. It's just turn this into a unit vector. All right. All right. So what we just saw here is if we have a basis that's orthogonal, can we make it orthonormal? We sure can. We just have to scale the vectors to unit vectors. So a question that we're going to look into after exam 2 is if we have any basis, including one that's not orthogonal, can we turn it into a basis that's orthogonal, and then, if necessary for coding, convert it into a basis as orthonormal? Can we do this with any basis? And the answer is yes, but it's going to take us a few days to build up the machinery to do that. Anyway, take care. Have a good couple of days. I will see you in the next video.